So that means in a VFF model you automatically get this change in lattice constants here, this biaxial strain. So you grow the red guys on top of the green guys, they need to stretch to the top in order to fit onto this substrate. Okay? So the lattice actually sort of stretches out to the top, that's called biaxial strain. And that comes out of a numerical calculation with a VFF model. You can do this analytical for sheets in these kind of forms, but if you have three-dimensional objects where some guys can push left and right and up and down, then you need to do it in 3 dimensions. So we have a 3-dimensional valence force field solver for 52 million atoms. And there's a big impact of strain on the conduction and the valence bands. It deforms the crystal, the band edges shift, and the degeneracy of light hole and heavy holes is lifted. For the conduction bands, you can sort of analytically write down things from continuum theory, where you have a conduction band deformation and a valence band deformation, and also a coefficient for biaxial strain. And that gives you an idea. These are some of the constants for indium arsenide. And that gives you an idea why we do the strain. Now I'm going to move on to the piezoelectric effect. We can derive a strain tensor out of these strain calculations, and if you have a strain tensor in a polar material, you have a charge density you can compute, and given the charge density you can compute an electrostatic potential, which you can then float into the Hamiltonian. Once you have a Hamiltonian with all the neighbors and the electric fields or magnetic fields, you can construct it with the equations I mentioned earlier, and you can calculate the eigenstates. The tough part about this is that we are interested in interior eigenstates, not exterior, and I'll talk a little bit about that later. And the key element is that all of this works from the bottom up in a parallel code in MPI. And that has been tested on a bunch of clusters. And the way we parallelized NEMO3D in the first place was we take a chunk of semiconductor, we slice it into slices, like this, like bread. Okay? So we divide the simulation domain in slices. That means we only need to communicate from one neighbor to the next. We don't communicate all over the place. Because if you talk, you don't work, right? If a computer talks to the network, it generally doesn't work. It needs to compute floating point operations. And a parallelization scheme like that would mean it ends up with a block tridiagonal system, and you repeatedly do a matrix vector multiply resulting in a vector. And you need to make this thing hum fast, really fast. Because you do that matrix vector multiply 2, 4, 6,000 times for 50 million, for a matrix that is 10 to the 9. Okay, so you really want to make that efficient. And we also wrote our own Lanczos solver that actually beats the standard solvers like Parpag or Zunger's folded spectrum method by quite a bit. Why did we do that? So here's a little anecdote you might like. So I was interviewing at JPL in 1997, and I told my boss to be, supercomputers are utterly useless for engineers. I was interviewing for the high performance parallel computing group. I got still hired, and my boss then told me, Tom Swig, said, well, you might change your mind. We're just developing something called Beowulf clusters. That was done at JPL, and one of the developments was done at JPL in our group there. So we had Tom Sterling in this group, who had won the Gordon Bell Prize in 1997 with the 16 Pentium Pros running at 200 megahertz, 128 meg of RAM, total 2 gigabytes in total, 5 gigabytes disk space, on a 100 base T network, and they won the Gordon Bell Prize right that year for the cheapest computing that was available out there and the most performance. So within a few years, that's what I really want to show. This has developed into commercial products within 5 years from, you know, concept, let's try this, hook PCs together, whether we can run parallel code to it, to something that you can buy, where you say you have 66 of these machines with a gig of RAM connected by 100 base T for around 100K, for $100,000. That meant supercomputers for people with problems to solve under their control. When I said supercomputers are utterly useless for engineers, I meant they're not accessible. I don't have control over them. I sit in a queue for a week and I have trouble. I don't have the software installed that I need to get my work done. It would take a month for that software to get installed because it's not under my control. Now, we're in 2009, quite some years back. Every supercomputer of the world is a cluster, whether you like that word or not. They might be internally highly networked, but the bigger boxes with 16 nodes, 256 nodes, whatever, they're clustered together. The world has utterly changed from I'm going to do my stuff serially to I have access to big computers. So the first scaling results here are the second scaling results in the sense I don't have the really old results on these slides. In 2000 we ran on a dual Intel Pentium 3 up to realistically more like 4 million atoms, up to 64 cores, and what I'm showing here is wall time of a benchmark. So wall time versus number of CPUs on a log-log scale. So if you want to do scaling on a parallel machine, you double the number of cores, you want to divide your compute time by 2. You double it again, right? That means a straight line on a log-log scale. So NEMO3D at the time was scaling quite well on the biggest machines we can lay our hands on. And then 2003 we ran on these Apple G5 cluster, also just fine, up to roughly 8 million atoms. And then in 2007, I wrote a proposal to drive this a step further, and we did a bunch of benchmarks of NEMO3D on a bunch of then available machines in 2007. We scaled NEMO3D to 8,000 cores on a Cray XT3 or in an IBM Blue Gene, and we ran on a bunch of other machines up to, say, 1,000 cores. So the core scales pretty well. But on this example here, I'm cheating a little bit. What I did is, and I mentioned this, that NEMO3D has a 1D slicing, okay? That means if I want to have 8,000 slices, and I have limited memory, that means I have simulated a really long nanowire that's very thin. Okay? This is not what I'm really after. All I wanted to demonstrate is that this kind of algorithm can scale to more than 8,000 cores.